Hello and welcome to CEO's Projects. Today we're going to go over how to design the resistors for a BJT so that it fits given parameters. In this case, our parameters are voltage gain at 20, voltage at the emitter 4 volts, voltage at the collector 8 volts, and the emitter current is 1 milliamp. Now, the values that I have are a bit different just because they use a real-life BJT. I do this for a lab. So, to start off with, we want to find RC and the equivalent of RE using the DC model, because those are very easy to find. Then we're going to go to the AC model, and we're going to find RB using a slightly large equation and some estimating. And then from there, we just need to do a tiny bit of testing to make sure our Rin is over 10K, just because that was one of the qualifications also for this lab. So I'll write it down now, actually. Rin is greater than or equal to 10 kiloohms. Now, for this lab, we were given a range from 1 milliamp to 10 milliamps, and it was found that going lower, closer to 1 milliamp, would result in a much easier numbers for Rin. So, starting off, we use the very basic equation. Since we know that here is 4 volts, we know that the E equals 4 volts, and VE equals IE times RE, so equals, so our collector current, or emitter current, is 1 milliamp, so 1 M times RE. Now, doing the math, you get RE equals 4,000 ohms. So we're just going to say it 4 kiloohms. So we already have RE. You find RE1 and RE2 a lot later. Now we're going to go to RC. Now we know that RC is going to be equal to essentially the voltage drop off of RC and IC. The thing is though, we don't know IC, so we have to calculate that. So IC equals beta over beta plus 1 IE. Now, plugging in the values, you have, oh, I forgot to write that. Beta is also 100 in this case. You have 100 over 101 times 1 milliamp equals 0.9901 milliamps. Okay, so now we have IC, we have VC, and with that we can find RC. So, since the voltage at this point is 8 volts, that means that there's a 4 volt voltage drop off of RC. So that means we have 4 volts equals ICRC, which equals 0.9901 times, and then we have times RC, and then doing the math, you find that RC is about 4,040 ohms. Okay, so we have RC, we're good for that section. We have RE equivalent, and we have, okay, so now from there, we now sort of build the steps for solving for RB. Because the thing is, if we find RB, then we can find RB1, RB2 fairly easily. So, going to this side a little bit, we have these two equations. RB equals RB1 times RB2 over RB1 plus RB2. Now, this equation we can't use yet. The equation that we can use, though, is first we need to find VB. Now, thankfully, there's a built-in equation into here. VBE, we know, is 0.7. That comes standard. So we have VB, which is the base voltage, equals VBB minus V. Oh, wait. Sorry. VE equals VBB minus VBE. Going down, that's 4 volts equals VBB minus 0.7. Doing the math, you get VBB equals 4.7 volts. All right, now we get to use the equation that I was talking about. So the equation is, in this case, VBB equals RB2 over RB1 plus RB2 times VCC. Now, the reason why we're able to do this is because this acts sort of like a voltage divider. So we can use this equation. Now, this equation is very important because since RB2 and RB1 can be split, it'll give us a direct relation of RB1 to RB2, which then we can use inside here once we find RB. So, just substituting some values, you have 4.7 equals, RB2 over RB1 plus RB2 times 12. Now, that might not be super readable, so we're going to switch back over here. So, what you end up getting is 0.3917. It's really 6 repeating, but we can just call that 7. Equals RB2 over RB1 plus RB2. Now, here's where the fun part comes in. If you multiply these two across, and then you subtract the RB2 from there, you end up with 0.3917 RB1 equals, I think it was some value of RB2. But in the end, what you end up getting is RB1 is sort of equal to 1.55 times RB2. Now, that is very important because this, when we plug into here, once we find RB, will give us both values, and that'll essentially have us just need to find RE2 and RE1. So, from there, we first need to find, the first thing we need to find is RE1 and RE2. Now, thankfully, since we know RE2 plus RE1 is RE equivalent. So, we can find RE. Now, there's a whole thing with voltage in the AC, but we were given this on the exam, or not on the exam, in the lab, where we have AV equals RC over RE plus RE. Now, it wasn't specifically stated, but through AC analysis, when you go and you do it out, RE1 ends up just being the only thing you can calculate for. So, RE1. So as you can see, we can plug in. The only thing is that we don't have RE yet. Now to get RE, we just have to do a tiny bit more finagling. Just hang on with me there. So, RE equals VT over VT over IE. Now, this is the voltage threshold, and over the emitter current, which we know what that is. So, equals 25 millivolts over, and then we have 1 milliamp. So that equals 25. So, from there, what we can do is we can just take that and plug it right into here. But we're just going to go a little bit farther. So, our pi, which we will be using later, equals beta plus 1 times RE. which equals 101 times 25 equals 2525. So that's our R pi. So now we have RE and R pi. Our pi will be very important when we end up finding Rn and Rb. So plugging back into here, we now have 20 equals 4,000 over 25 plus RE1. Now, it is found that in this case, RE1 happens to be 177. So, ohms. So, like I said before, these two add up to RE total. So, I'll just do the numbers. So, we have 4K minus 177 equals our value, which is 3,823 ohms. So RE2 equals 3,823 ohms. Okay, so now, just backtracking, we have RC, RE1, RE2. We also have R pi and RE. Now, here's the fun part. There is a very, very large equation that we can use to get an average of Rn. Now, Rn, in this case, we're going to set equal to R sig. So, let's just say R sig happens to be 15 kiloohms. Because that is far enough away from Rn being greater than or equal to 10K, but it's also not so high that we have a voltage offset. So, what we're going to do is use this one large equation, which is comprised of two smaller equations. I'll put each smaller equation on there. So, we have Rn AC equals RB in parallel, which is the 1 over something plus 1 over something inverse equals the value. So that over R pi, which is what we were able to calculate up there, plus beta plus 1 RE1. So we now have that. Now going through, you end up finding that it's close-ish to about 10K. So, sorry. So you have that one. Then you have RNDC, which is the same exact equation, except that is the total resistance. So RB Okay, so you can take those two, add them together, and divide by 2 to get the average. So, throwing this all together, we're almost there. Rn equals RB in parallel with R pi plus beta plus 1 RE1 plus RB in parallel with R pi plus beta plus 1 RE. 2, 3. Yeah, we'll say that's that. And then we have all of this divided by 2. Now, the thing is, we don't know Rn and Rb. But to make sure that there is a voltage drop of 1/2, we're going to set we're going to set Rn to R sig. So we can say here that 15K equals, and then essentially all of this you just plug in, and you're going to find that in the end, RB is going to equal close enough to, actually, you know what? We'll write it out fully. So, 15K ohms equals 1 over RB plus 1 over, and here we said it was 2525, 2525 plus 101 times 177 plus that negative 1, by the way, is what I'm saying the inverse, because that is equivalent to that. So 1 over RB plus 1 over 2525 plus 101 times 4,000. Negative 1 over 2. Okay, so when you plug this into your calculator, you should end up getting RB is about 20324.2 ohms. Okay, so we've finally gotten RB. Now we can use this equation right here, and we're essentially done. We just have to do a tiny bit of checking, but that's it. So we have our equation from up here. Since we have RB1 equals 1.55 RB2, you end up with RB equals 1.55 times RB2 times RB2 over 1.55 RB2 plus RB2. Simplified is 1.55 RB squared over 2.55 RB2. All right, and that equals what we just found, 20324.2 ohms. Now, throwing this into the calculator, you end up with RB2 equaling 33,436 ohms. Okay, and then literally you do right there, you just multiply RB2 by 1.55, and that gives us RB1 is about equal to 51826 ohms. Hooey! All right, so we've gotten RB1, RB2, RE1, RE2, and RC. And by setting the RSig to 15K, our Rin is 100% over, over the given limit. Now, if you were to model this in multisim, you'll find that if you measure here as your V out, this should be close to, I'd say about 5% either way, of about 400 millivolts. And then measuring here, you have 20 millivolts, and AV also is V out over V in, which when you have about 400 millivolts, in my case I had about 390. Actually, in my case I had 385 millivolts over 20 millivolts. And that equals about 20, which is what we wanted. All right, so after simulating and collecting the values, we found emitter current, 975 UA, which is 0.975 milliamps. VE was 3.9 volts. VC, 8.09, and then, well, the rest. So, we're going to see what each percent error is. Now, I've calculated on here. It's a lot of writing, so I'm just going to give you the basic formula, which is actual minus calculated over, and since our calculations should be right based on the fact that this is a non-ideal system, we're going to actually have it over calculated and times 100. So we're going to have this right here. We'll do it right on the edge right here. So this is our percent error for each. So we found that there was only 2.5% for the emitter current, which is fairly good. We found the same exact percent error for the emitter voltage. We found a half that voltage, so 1.125% for the collector voltage. We found a 3% error with the base voltage. We found a 3.75% error with our V out. There's actually 0% error with these two, but that makes sense because we're measuring it straight off of the supply. So we had a 3.75% error. At the Rin, we measured a 1.5% error, and our voltage and our gain was a 3.75% error. So, going through what we had and going through what we have now, you can see that having a percent error of less than 5% on every single thing we calculated just shows that, well, you got it right. We know that our Rin through calculation and measurement is over 10K, which is exactly what we wanted. We have our voltage, our base voltage, or our emitter voltage very close. Our collector voltage also very close. Now, one thing you can notice is that the emitter voltage and the collector voltage are both off of their respective values by the amount that, well, they're off. So in other words, this being about 0.1 off is also equal, or essentially that 0.1 could go right there. Now, you could do some messing around, some tuning, and you could get it closer. But again, this is not ideal, and the values work, so once you get the values to work, you want to stop messing with it. So, what else? I mean, that's really it. So, as you can see with our results, they're right. Now, I'm going to just quickly go into the explanation of how RE, I don't have it written down here, how this RE just becomes itself. Actually, not that. I think I'll cut it here then. So cut here and then where are you going? So, all right, so with everything that we had, we were able to calculate all the values given right here, and also, just in case you skipped the end just to figure it out, we had RC equals 4 kiloohms, RE1, actually no, RE equivalent equals, oh, sorry, I also got that wrong. And then we found that RE1 equaled 177 ohms. RE2 equals 3823 ohms. RB total equals 0.324.2 ohms. RB1 equaled 33436 ohms, and RB2 equals 51826 ohms. And we also found out that if we set our R sig to 15K, our Rn was fairly close when using that massive formula, 15 kiloohms. So, thank you so much for watching. I hope this helped clear something up. I do this for a lab, and once I finally figured out what to do, everything became a lot easier. So, subscribe if you want. I do this for fun.